this, well, this and to proportion. So this is two sample where you're doing means, not proportionality, where it's like percentages. We'll do percentages next week. But this is what most of your science things are, unless you're doing something like Dylan did, where he's trying to compare it all at once, which is a nova is probably the better one. You chi-squared works too,
Oh, yeah.
which you guys learned some chi-squared. Apparently, Dylan did his own research to do a nova and what it means.
Yeah, got it.
Hopefully, you interpreted it correctly. Like, that's kind of the big thing with any of these is can you interpret them correctly and set them up? Like, I can teach you how to enter this into your calculator in 3 minutes. Okay. We will. We're not calculating this one by hand, period. Okay. Like, I made you do the calculations by hand in chapter 10 to kind of get the idea of what are we actually doing so you can learn to interpret these statistical analysis correctly. That kind of makes sense. But basically, we're done doing statistical analysis by hand. You get a calculator on your exams. I expect you to use it. We will work on how to notate the work of what you put in your calculator after spring break. When we do some practice exams, we'll take a look at how they're putting those things in and what they're looking for. So, two sample problems are two independent populations. In most cases, it's your experimental and your control group. Okay. Those are two separate populations. It might be from the same population, but you gave them different treatments. So they are the effect on different populations. A matched pairs is not a two sample. That is one of the most common errors that gets made. Matched pairs, you take them, you match them, you find the difference, and you do a one sample. Two different treatments on two different sets of people. So it's two different populations. Hmm. The populations might be different treatments, but they have to be different people, not different treatments on the same person. So, a medical researcher is interested in the effects of blood pressure of added calcium in our diet. She conducts a randomized comparative experiment in which one group of subjects receives calcium supplement and the other gets a placebo. Two sample. Okay, different subjects in each with different treatments. A psychologist develops a test that measures social insight. He compares the social insight of male college students with that of female college students by giving a test to a sample of students of each gender. Two clearly different sample populations. A bank wants to know which of two incentive plans will most increase the use of its credit cards. It offers each incentive to a random sample of credit card customers and compares the amount charged during the following 6 months. Okay. That's to each of its incentives to a random sample of credit card customers. I think those are two separate samples, so two populations. I was wondering, I was going to be curious if they did 6 months of offer one and 6 months of offer two and did matched pairs. I was trying to read really carefully. Okay. Yes, I do need you guys to speed up your test taking, but I also need you to read carefully. That makes sense, especially in statistics. make sure you read carefully and understand what the question says. Yeah, but maybe you randomize who gets which one first. So the randomization and matched pairs would be what order do you get offer one versus offer two? And when this was written, credit card rewards was like a new thing. So trying to get people to use their credit card by offering them rewards for using it or something. So conditions. We have two SRSs from two distinct populations. The samples are independent of each other, and that is one sample has no influence on the other. Matching violates independence. Okay. And this is going to do all the calculations. I'll show you a little bit of the formula, but basically, you're going to use your calculator. Both populations are normally distributed. Means and standard deviations of the populations are unknown. Remember, central limit theorem said doesn't matter how big with t-tests, 40 or more is normally distributed. The means will be normally distributed for 40 or more. Well, with this one, it's even lower. You can do, unless there's evidence that it's not normal, you can get away with doing this with 5 in each sample. If you have 20 in each one, totaling 40, plenty big. Ideally, your sample size from each of the two samples should be pretty similar. A lot of times in reality, they don't come out perfectly. You guys did your bio IAs. Did anybody have any plants that didn't come up or anything that didn't?
Yeah.
And so you didn't have exactly the same number in each part?
I still put it on just to keep that there because I felt because like a part of my experiment was seeing if it didn't grow due to the like inhibition of growth.
Okay, so that would be part of it.
However, a lot of my plants in my control still didn't grow, so I have to talk about like the variability in seeds. But I decided to include those to keep that up there and not like kind of like take out data results for
Yeah, and that makes sense. But if if you're not doing something that should kill seeds or make like if you were testing maybe this is supposed to not allow things to grow, then seeds that don't grow are just, well, that was a defective seed. If you're doing something that it's supposed to enhance growth, anything that doesn't grow, well, we just not include them. So oftentimes sample sizes don't end up the same, or somebody drops out of the test, or well, I was supposed to take this pill every day, but I didn't. I kept forgetting. Well, then your results aren't going to be good. So I can't include you in the test. So practically speaking, a lot of times they're not actually the same, but they should be close. Ideally, you're going to start with them close enough that they still end up close at the end. Does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. The relationship was strongest for Black men. Such observational studies do not establish causation. So, researchers therefore designed a randomized comparative experiment. The subjects were part of the experiment were 21 healthy Black men. A randomly chosen sample of 10 of the men received a calcium supplement for 12 weeks. The control group of 11 men received the placebo pill that looked identical. The experiment was double-blind. The response variable is the decrease in systolic blood pressure after the 12 weeks in millimeters of mercury. And increase appears as a negative response. So here we have our decrease, some of them increased. Here with our placebo, we have our decreases and some increases. In general, people that would do a study like this are probably trying to reduce their blood pressure. So there might potentially be trying other things as well. So hopefully they're all going to have some decrease, but there's just some variability in this. Um, there's often things you can't control, like stress and stuff. So the calcium group shows a drop in blood pressure of 5, while the placebo group had almost no change at negative 2.73. So they went up. Is this outcome good evidence that calcium decreases blood pressure in the entire population of healthy black men more than the placebo does?
Let's see.
You're going to guess yes. But do we know?
Not without running a test.
Not without running a test. We'd like this could be maybe that's just within random variation. I don't know how wide random variation is without running the test. Because I mean, in this control group, you see some 12s. I guess you see a negative 11. This one, you've got some negatives. And we're looking for evidence on average. There's obviously lots of other things that do this, but if on average it helps, we're going to tell people to take calcium because that's a pretty easy thing to take. It doesn't seem to have much for negative side effects. I'm sure somebody's allergic to it somewhere, but so identify our population of interest. Our population of interest is black men with high blood pressure. So H naught mu1 equals mu2. The mean decrease in blood pressure for those taking calcium is the same as the mean decrease for those taking the placebo. Mu1 is greater than mu2. The mean decrease in blood pressure for those taking calcium is greater than the mean decrease in blood pressure for those taking placebo. You will sometimes see this notated as mu1 minus mu2 equals 0. They're just subtracting mu2 to the other side. Is not equal, well, then it becomes a two-tailed. So in this case, we were doing, if here's our mu1, mu2's mean falls somewhere over here. And so you end up with, essentially, it's going to calculate it down into something like this. If you're doing two tails, you still double it. Okay, so not equal is two-tailed in all cases, one sample or two. Not equal can be either side. It's far enough away on either side. Yes. Yep. Does that make sense on this notation thing? That it's just you subtract u2 to the other side. Good luck, Devin. So you can say equal to 0. Like I like this notation better. That's what I would use when writing them. Occasionally you'll see this written out, and you just need to know that that's the same. That makes sense? I don't encourage you to use the notation on the right. You can if you want, I don't care. But you just need to know that you can convert it between these two, and they mean the same thing. That's not me trying to say, hey, use this notation, it's better. No, it's me saying, hey, you're going to see this. Okay. So we need to verify our conditions. Because of the randomization, we are willing to regard the calcium and placebo groups as two independent SRSs. Okay. And is any experiment truly random? No, you probably don't randomly select your subjects. But because you randomize who goes into which group, or with matched pairs, who gets which one first, we're generally willing to consider that an SRS. Okay. Is people that are willing to volunteer for a survey maybe fundamentally different from the general population? Yeah, but probably not fundamentally different from the general population that's actually trying to reduce their blood pressure. So our population of interest might not be all black men, but it might be black men trying to reduce their blood pressure. There are some with high blood pressure that are like, whatever, I'm not changing anything. Black, white, any color, but that makes sense. So yes, our population might be those that actually care. So we need to check for normality. They chose the back-to-back stem and leaf plots. Those both look reasonable, normal enough. Okay, if we've got sample sizes of 10 and 11, that's plenty large. There's no extreme outliers or extreme lack of normality. It will not look like a good, perfect, normal curve with sample sizes this small. That makes sense. The placebo is pretty tight in the middle, but yeah. So it hasn't showed us how to calculate yet. If we're doing a confidence interval, so you're going to take the two means and subtract them. This one was 0. It's almost always 0. Like, you're testing, are they different? Mu1 minus mu2 is 0, which is, I think, sometimes why they'll take mu1 equals mu2 and subtract the mu2 from both sides and get this, because that's what goes into the formula nicely.
Wait, but in this case, mu1 minus mu2 is 0. So
Yeah, it is. They're supposed to be the same. The Why isn't it just 0? Because maybe there's a case where it's not. You want to know, is the difference greater than 5 or something? Where you're not just testing if it's 0? I can't think of a specific case, but maybe you're trying to say, is this one, maybe you've decided that it's not worth it unless it's at least 10 more for whatever purpose, whatever experiment. It's not worth spending money on this fertilizer unless it produces this much extra growth.
For the echo or the mu? Because if it was mu, I don't understand how it equals.
The numbers they gave you were the X bars.
Okay.
Mu is what we're trying to draw conclusions about. So mu is always coming from these. Mu always comes from your H naught and your HA. The numbers they gave us are the X bars. That makes sense? Like the means that they give here are the means for the samples. Dylan, that makes sense?
that's what I'm saying how it's 0, because is it mu? So for H naught, it should equal 0, but what about for H alternate? What equals 0?
When you use the formula, you're always using your H naught values. Okay. Wednesday or Thursday? I was like, I'm meeting with you guys to discuss your outlines on Tuesday. And like, you can go meet with Mrs. Wright and meet with me both in the same period. So it doesn't really matter. Like, I just need to know if you're going to leave. So if you're leaving at the end, so I do get you in before that, or if you're leaving at the beginning, we'll get you in after. Does that kind of make sense? So when you're looking at these formulas, and I'm not sure why they're giving us the Z formula instead of the T. The only difference here with T is usually mu1 minus mu2 is 0, but it's not guaranteed. Yeah, like bring it to Mr. Klein's class. Abby, can you take that to Mr. Klein's class? Thanks. I think Ivy's at the office too. I think I saw her walking down. So the standard deviation, remember how we had to add variances? When we added standard deviations, this didn't go that well on the last test. You add when you're trying to get the standard deviation of two things combined, you have to add the two variances and square root that. So it's kind of like a Pythagorean theorem idea, where you have to square them. You have to square the two standard deviations, that's variance, add them, and then square root it. So this is just how we add. And because they were both, it was s over square root of n was your default. When I square it, I get s squared over n, and then I have to add the two of them together. And then square root that, because kind of like a Pythagorean theorem idea.
And this is the fine.
That's to find the test statistic. This. So I'm just explaining why the bottom is what it is. So it's again just x bar minus mu over standard deviation. So I'm just, x bar is now the difference in x bars. Mu is the difference in mu's. This is how you get standard deviation with two of them. You add the squares of both parts. There is a two sample Z test. What's the difference between Z and T? When would you use Z?
Yeah.
So if you know the population standard deviation, which isn't common, but pay attention to that because they might give you a problem that does. Okay.
So when we do the population.
When you know the population standard deviation. If you know the population mean, you don't do inference. You just say what it is. Because inference is all about the population mean.
Okay. But if you have the population standard deviation, which you normally don't,
then you use Z. If you don't have the population standard deviation, you use T. So sometimes we'll say population standard deviation. If sigma is known, if you look in Z, there's a sigma. If you actually know what that is, you use Z. If you don't know what that is, you use your sample standard deviation.
okay.
And when we do it with proportions, there's a way of calculating sigma. There's a formula for it, so we use Z.
So with this, it's supposed to be the population sigma.
The Z one is. The T one is that I wrote on the side is sample standard deviation. And you use a different distribution. Basically, you select a different one on your calculator or statistics software, or Google Sheets can do all these basic ones. So that is your hint as to which one you select when you go to the calculator. Oh, hey, they've got it here for T. The standard error is always technically with the standard deviation. How did you get degrees of freedom for a one sample t-test?
N minus one.
N minus one. Simplest way to get degrees of freedom for a two sample, and it's not the most accurate, but it's always at least this, is take your smaller sample size minus one. So if we had a 10 and an 11, so we do 10 minus one would be 9. I'm gonna skip ahead a little bit and show you where is it? That's the formula for actually calculating degrees of freedom. You can just let your calculator do it for you. Your calculator is going to ask you to do, so because this formula was a little gnarly, the shortcut when people were doing it by hand was take the smallest one and do minus one. Now, the higher the degrees of freedom, the narrower your curve gets. So something might go from fail to reject H naught to reject H naught by just changing the degrees of freedom. So one trick they used to do, and your calculator will ask you if you want to do this, is called pooled. Pooled would mean you can pool if you assume the standard deviations are the same. If there's no reason to assume they're different, a lot of times they would pool, and then your degrees of freedom would become n1 plus n2 minus 2. So instead of just taking the lowest one, you'd actually get to add both of them, which again tightens your curve, which then allows you to conclude sometimes that things are significant when you wouldn't otherwise be able to. You should only pool if the problem tells you to pool. There is a checkbox on your calculator. Okay, but that's what it was for. This was a lot of these systems were came up with when statistics was all done by hand. People were using glide rules and then, 4-function calculators. And so running this formula, thanks, would be a bit of a pain. Okay. Now, you're never going to run that formula in your life. Pretty sure I did not assign you a problem to do this. So, continuing this, we are going to, I guess I'm just going to input the data. We're going to do this with data input because instead of just reading the problem to get the things. So we go to our calculator, go to your calculator, add a list and spreadsheet.
And we're gonna grab a book so you all have the data.
List and spreadsheet.
I don't feel like having to switch back and forth and then let you switch back and forth and let you copy. So this is page 651.
Tell them it's gonna do something. Let's see.
They tell them they're getting a pill. They tell them they're getting a calcium pill. Well, I mean, they tell the groups that one group is gonna have a placebo and one group's gonna have a calcium pill.
They don't-
But you don't know which one you're in. So that there's not other effects. So now we've got that. We should probably do our check for normality. So I would add I mean, they already did it by hand, but to do a check for normality, I would just do a data and statistics. And I would do this, calcium, and I would do plot type. I would do normal probability plot. Menu, plot type, normal probability plot.
Which one is plot do? Like,
So when we're assessing normality, you have to have something to assess normality. The dot plot wasn't great because it was just everything's on a level of 1. It doesn't, you could have also done a histogram. Follow the line. If they sort of follow the line, you're good enough for this test. I don't like histograms because you have to, there's histogram. That's also normal enough. So you should check normality on both of them. Wow. That one's
yeah, I was gonna say.
I think with sample size 10 and 11, this is close enough, but
Yeah,
that one's not that normal. So the placebo did. The placebo looked better than the calcium.
can we call calcium normal?
We can call it normal enough for sample size 10.
We're just not.
I was like, it looks a little, so depending on how you do your bins, but yeah, this is kind of low in the middle and like it's a little, but it's for sample sizes. I probably would not be okay with this at 5, but sample sizes of 10, yeah, it's such small amounts of data. Like you don't really get normality well until you get into the hundreds. So you should expect some level of variability. It's not extreme. There's no big outliers here. Like we got a couple down here together. Yeah, there's a little gap. We got some in the middle. We got some here. And these aren't that far below 0 either. So now to actually run our test, we're going to add a calculator screen. We will do menu statistics. You could choose this confidence interval if you wanted. I feel like doing a test because that's what it was doing. And I want a 2-sample t test. I'm going to choose data. I don't have this in statistics. I entered my data. List 1 is calcium. List
We know which one this one is too.
doesn't really matter. It does matter because we listed, we're calling mu1 the calcium group. It matters on this one. This is where it matters when we set the alternative hypothesis. Calcium was supposed to have a higher reduction score than, so it matters that that goes the correct way with HA. Pooled, no, unless it tells you to.
Oh.
Okay. So important piece of information, my test statistic. 1.6. My p-value 0.06, my degrees of freedom. So p-value is just above. So the experiment found evidence that calcium reduces blood pressure, but the evidence falls short a bit of the traditional 5% and 1% levels. We fail to reject H naught at either of these significance levels. So I'm with this case, I might be perfectly willing to, and I like how they worded that it found evidence. This is just a calcium supplement that I can buy at Costco for. I can take calcium, magnesium. I get 500 pills for $12. Supposed to take one a day. That's enough evidence that I would do that. Okay. If this were a new cancer treatment with several negative side effects, probably not good enough evidence. Okay. But this fell short of the traditional levels. What would have probably made it get there? Larger sample sizes. If you could have gotten 20 in each group, now why did they only have 21 total? Probably how much budget they had, and they probably had to do some level of paying these people to do it, or paying for their treatments or something.
How much money do you think on average, a study like this would give out?
12 weeks, probably a couple hundred. You're probably going to get people that are very interested in this, and regardless, interested in reducing. But like when I lived in Seattle, there was some, and they'd have advertisements on the radio for blah 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 during the study. They'd usually pay a couple hundred to 1,000, but you'd have to drive from Seattle to Tacoma, which is a 45-minute drive in good traffic, maybe an hour and a half each way, probably once a week. Depending on what it is.
No, because like any study that they want, they're not taking.
Depends on what it is. It depends how far you have to go.
Yeah, but like when I'm in college.
In college, you probably could just walk across campus. So that's why a lot of tests are performed on college students. The two sample confidence interval is basically what a one sample is, except remember it was always estimate plus margin of error. Estimate here. Well, now my estimate is my difference in the X bars. This chunk here, margin of error. Well, the standard deviation formula or standard error formula in this case got more complicated because I'm combining two of them, but otherwise it's the same formula.
But our calculator does.
Your calculator does that, yes. Okay. If they give you the statistics, the X bars and the S's, then you do stats and you just enter them. That makes sense? Your calculator, the formulas, it's good to have, I've seen them understand what they mean and why they are.
I don't understand what T star is still.
T star, that is related to the confidence level.
I just don't remember.
Okay, let's talk about it. So, and this is where that shortcut on degrees of freedom might be helpful. If you had the n-1 from the smaller one. Let me go open the formulas. Did I put it in here? Yeah, I did. So T star. So this would be 9 degrees of freedom because the smaller n was 10. If we're looking for a 95% confidence interval, that's the Z table. Looking at our 9 degrees of freedom, 95% is going to have a 0.2025 on the upper tail because it's 0.025 on each of the two tails. Confidence intervals are always two-tailed.
Like 0.025. On the other side, you had 2.5. Did you just do like percentage for one of them and probability for the other one? Is that-
If I wrote 0.25, I probably meant 0.025. That would have been me screwing up. Was that the one yesterday?
Or, I don't know if it was 0.25, it was like 0.5
I-
on that side and 2.5.
Side and 0.025.
Oh yeah, one would have been a percentage then, yeah. So yeah, sometimes I'll say it as 2.5% or 0.025. So the T star here is this. The T star is the scaled value for how far away you are in standard deviations, essentially, for to be at 95% confidence. Or if you notice that value, so with 15 degrees of freedom, that value goes from 2.26 to 2.13. What is that going to do? It's going to narrow my interval. That's why that formula would become valued. If it was pooled, it would have been 19, 2.093. Not a huge difference there. But having that becomes very valuable because all of a sudden oh, that does make a difference. It's not a huge difference, but this calcium wasn't quite enough, even with the higher degrees of freedom. Yeah, so to use the calculator to get this, because you're not going to get this table, you just use the calculator to do it anyways. But if you needed the T star, menu, probability or statistics, distributions is under both of them. This is going to be inverse T. Area 0.025, degrees of freedom 9. That didn't do anything. I guess I didn't have it clicked there. No, that was my previous thing. I was clicked in the box, so it didn't take it. There's my 2.26. We drop the negative because it's plus or minus. Doesn't matter. If you did 0.975 for the other one, it would give you that. It usually, well, the T table that it has gives it. This is not doing it the opposite of the T table of the Z table. This is doing exactly the same. That's why the lower one was negative. Because the lower side of the Z table is negative. So this is showing it as upper probability. Z is showing lower. The calculator was showing lower because I put in 0.025 for an area that's on this side. But again, they're symmetric. T stars and Z stars, we always plug in the positive value. The confidence interval is this. It does overlap 0, meaning we'd never have a significance at 0 at this 95% or 5% level. Even when we did the one-tailed 0.05, it still was overlapping 0. Remember, 0.05 one-tailed is like a 90% confidence interval because it's 0.05 on each side. Robustness, part of the great thing about the t-test is you can kind of sum the two sample sizes to get them. And remember, normality with 40 total was plenty, but 20 only needs a little bit of normality. Once we kind of surpass sample sizes of 10, 12, 10, 12, you need reasonable normality. But once we get beyond that, and you can do the combined total for getting to that idea of 40. At 20, unless it's really bad, you just go with it. And ours kind of looked bad, but it wasn't bad enough that we can't run a t-test. T-tests are also more robust than Z, meaning normality doesn't have to be as good. So getting more accurate here, that's what we did. We did the calculation with it more accurate. Your confidence interval narrowed a little bit from 0.783 to 0.491. Still not enough to make my conclusion, but that more accurate degrees of freedom gave me something better. We're going to do one more example. DDT poisoning. DDT poisoning causes convulsions in humans and other mammals. Research seeks to understand how the convulsions are caused. In a randomized comparative experiment, they compared 6 white rats poisoned with DDT with a control group of 6 unpoisoned rats. Yeah, DDT is a pesticide.
No, like deep water.
No. Electrical measurements of nerve activity are the main clue to the nature of DDT poisoning. When a nerve is stimulated, the electrical response was a sharp spike followed by a much smaller second spike. The experiment found the second spike is larger in rats fed DDT than normal rats. So this is the volume of the second spike in the experiment group and control group. Now, what we're going to get here is, instead of us plugging the numbers into our calculator, they gave us the output. Okay, and this happens on occasion. This book likes to do that. It's possible that you'll get a statistics software output on a IB exam. I feel like for the most part, they're just going to have you do it in your calculator. But if it's a large set, if it's like 40 or 50 in each one, they're just going to give you the output or they'll give you the stats. Okay, they're not going to make you enter 50 in each list. So we look at these. We can see we have different means. We have different standard deviations. If I'm running a test, I would use H naught this. Okay. So looking at my output, I've identified my population of interest. I've randomized the rats, so I'm willing to assume they're SRSs. My normal probability plots look fine. So I can proceed with this test. These actually look pretty good, which is good seeing as the sample sizes are really small. They're only 6 each. I don't know why they did so few rats, but maybe that was all they could afford. So we carry out the procedure. We look at this. Now looking at this thing, unequal variances. This means not pooled. And they use the degrees of freedom formula. So we get T of 2.99. We got a p-value of 0.0247. Okay. This key thing is variance is unequal is what you'd want to use, unless they tell you to pool, which that would be the equal case. You pool when the variances are equal. So I've got a p-value of 0.0247. What does that mean?
H naught was rejected and H ultimate was accepted.
So we conclude that I need to look at this. This just said they were not equal. So this is a not equal case that the low p-value is strong evidence against H naught. We reject H naught and conclude that the mean size of the secondary spike is different. They should not be saying larger. Is different in rats fed DDT. They maybe should have went, it increases it, mu1 is greater than mu2. But based on what they said for hypotheses, they should be concluding is different. Okay. It was larger in here. Sometimes you set up those hypotheses beforehand. Your conclusion should be it's different. The evidence from this test seems to indicate that it would be larger. You could say that. Does that make sense? A lot of times you'll set up your hypotheses though before you run your experiment. You maybe didn't know that in bio, but that is something you should do. Abby will know that for next year because we're doing stats next.
I'm sorry.
They didn't know that they should have set up their hypotheses for these tests beforehand. Several of them, bio and math, it's good to have that for. And yeah. So pooled is not much different. Okay, that's 11.2. That's 2 sample. Next week we do this with proportions. It's not a big step. You just select different ones on the calculator. There's a couple of different changes in the assumptions. That's 12.1 and 12.2. You'll do calculus last. We probably won't finish stats. She's gonna finish unit 3 by spring break. So a little ahead of you guys. We started calculus before spring break. So
Wait, so is this the hardest statistics thing? So they said 10, 11 chapters of statistics.